In this review problem, let's take a look at the differential equation y double prime minus x times y equals 0. And we're going to find a series solution for this differential equation about x equals 0. First, let's find a recurrence relation for the coefficients. To do this, we first start by writing y as a series about x equals 0, so n equals 0 to infinity, a sub n times, let me write it out in full, x minus 0 to the n. That's what it means to be a series about 0. And of course, we're not going to write that out every time, so instead we'll write this as simply a sub n times x to the n. Okay, now let's figure out what y prime and y double prime are. Y prime, if I take the derivative, I get summation n equals 0 to infinity of n a sub n x to the n minus 1. And of course, if n is equal to 0, this is equal to 0, so I can start the sum instead on 1 without losing anything, because the n equals 0 term doesn't contribute. Now for this problem, that's not all that important. Y double prime, of course, is going to be needed. That's equal to summation n equals 1 to infinity. If I take the second derivative, I get n times n minus 1, a sub n x to the n minus 2. Again, if n equals 1, then I get 0 from this part, so I can start this sum on n equals 2. And there won't be any problem, because if n equals 0 or n equals 1, then this first part gives me a 0. So that's in y double prime. Okay, the other thing that I need is the x times y. So if y is given here, then x times y will be equal to summation n equals 0 to infinity a sub n times x to the n times an extra x, and so that'll be equal to summation equals 0 to infinity a sub n x to the n plus 1. Okay, and so let's take these two things and subtract, so that y double prime minus x times y is equal to summation n equals 2 to infinity n times n minus 1 a sub n x to the n minus 2 minus summation n equals 0 to infinity a sub n x to the n plus 1. Okay, now to find the recurrence relation, I would like to combine these into a single sum. To do that, I would like to get x to the n for both of these instead of n minus 2 or n plus 1. So I will employ the trick that we've used several times where I re-index the sum. So this is going to be n equals 0 to infinity n plus 2 n plus 1 a sub n plus 2 x to the n. Let me briefly describe why this works. If n equals 2, then I have a 2 minus 2, 0 here. If n equals 0, I have x to the 0 here. So those match. If n equals 2, then I have 2 times 1. If n equals 0, I've got 2 times 1. If n equals 2, I have a sub 2. If n equals 0, I have a sub 2. So these match up. And this can be done more slowly using a change of index. For this part here, this change of index is not as common as the ones we've done in class, so let me do this one a little bit slower. So for this one, I can let k be equal to n plus 1, which means that n is equal to k minus 1. If n equals 0, that means k is equal to 1, and of course if n is infinity, then k is also infinity. And so this second sum becomes summation k equals 1 to infinity, of a sub n becomes a sub k minus 1, and then x to the n plus 1 becomes x to the k. And then I can change this back to n's, so n equals 0 to infinity. The first sum stays the same. And then the second sum, let me change it back to n's, n equals 1 to infinity a sub n minus 1 x to the n. Now I will combine these, except for one little catch. The second sum here starts on, the first sum starts on 0. The second sum starts on 1. So let me peel off the n equals 0 term here. If I plug in n equals 0, I get 2 times 1 times a sub 2 times x to the 0. And then what's left is summation n equals 1 to infinity n plus 2, n plus 1, a sub n plus 2 x to the n, minus the second sum, which is unchanged, So here I'm peeling off the n equals 0 term and then starting on n equals 1 instead. So I have 2a sub 2. And then finally I can combine these. I get summation n equals 1 to infinity of n plus 2 times n plus 1 a sub n plus 2 minus a sub n minus 1 times x to the n. And so that is the series for y double prime minus x times y, and that's supposed to be equal to 0. So the first part is find the recurrence relationship. Well, for this to be equal to 0, then this has to be 0. So a sub 2 has to be 0. And also this has to be 0. So n plus 2 times n plus 1 a sub n plus 2 minus a sub n minus 1 equals 0. So for this power series to be 0, the constant term has to be 0, then every coefficient has to be equal to 0. Okay, now let's solve for the higher index. N plus 2 is bigger than n minus 1, so I'll solve for this part, and that gives me that a sub n plus 2 is equal to a sub n minus 1 over n plus 2 times n plus 1. Let me now re-index this. This is not absolutely required, where the first term is, the index has a sub n on the left-hand side as opposed to a sub n plus 2. To make this happen, everywhere I see an n, I'm going to replace by n minus 2. So n minus 2 plus 2 is n. n minus 2 minus 1 becomes a sub n minus 3. A sub n minus 2 plus, n minus 2 plus 2 becomes n. Then n minus 2 plus 1 becomes n minus 1. And so that is the recurrence relation for this problem. Let's continue looking at this exercise. Part 2 says, describe how a computer program, say Excel, Mathematica, C++, compute the coefficients. So which basically means how do I implement this recurrence relationship, a sub n equals a sub n minus 3 over n times n minus 1, using a computer program. So to do that, let's pretend that this is Excel. So I'm going to do this with Excel. You can do any program you wish, but for simplicity's sake, I'll implement this with Excel. So we have the first column A, second column B, then we have row 1, row 2, row 3, row 4, row 5, row 6, row 7, row 8, and so on. Okay, so to implement this, in our first column here, we'll have the 0, 1, 2, 3, 4, and then that's going to be the numbers over here in the left column corresponding to the values of n. And this can be implemented fairly quickly, instead of doing this, by writing a set equals a sub 1 plus 1, and then filling downward. And then that would give 1, 2, 3, 4, 5, 6, and so on down here. All right, then over here in the right column, the value of a sub 0 and a sub 1 go here. So this is going to be the 1, that'll be 2, 3, 4, 5, and so on. A sub 2 we found to be 0 in the recurrence relation from the constant terms, so there's going to be a 0 here. Then after that, the relationship was that a sub n was equal to a sub n minus 3 over n times n minus 1. So to make that happen in Excel, this is going to be equal to a sub n minus 3. That means the term that's 3 back. So this is going to be equal to b sub 1. So 1, 2, 3 terms back, divided by n. So that's going to be the number that appears here, a4, times n minus 1. Now I can write either a4 minus 1, or else I can write a3. And then I will fill this down. And then by filling this pattern down, if I choose numbers for a sub 0 and a sub 1 up here, and then fill this pattern, that is a fast way using Microsoft Excel to be able to figure out the first few terms, or many terms, of the series expansion.